This is TMUA 2020, paper number 1. Let's get straight into it. Just a simple differentiation question to start with. We first need to deal with this, making into the powers, so we can use power form. X root x, well, that's x to the power half, times by x to the power 1, add the powers to get x to the 3 over 2. Then, of course, this is division, so we take them away. 3 take away 3 over 2 is 3 over 2. It's like 3 take away a half. Of course, also do 1 divided by 2 for a half, and then 5 divided by 2 for 5 halves again. 2 take away 3 over 2 is a half, and then this is the form that we can differentiate. So the differential of this is going to be 3 over 2 times a half, which is 3/4. Again, just doing standard timesing fractions things. 3 halves take away 1 is a half. I don't think I need to go over this too carefully. The only thing here is that we need to get it back into one of these to make it look like this. You notice there are all the roots here, so I need to put that in there, but it's also all under a shared fraction. So let's make the shared fraction over a 4 first. And now I need to get all the x's back to roots. So this is root x. This is 1 over root x, but I think the easiest thing to do is just to divide the entire thing by x to the half. Because then I'm saying x to the 1 divided by x to the half is x to the half, and x to the 0 divided by x to the half is x to the minus half. So this is the form I want it, but that's of course root x, which gives me this one here. So a little bit of work to do to get it into the way that they want it, but otherwise a fairly standard question. Question number 2, we just need some factor theorem here. If x minus a is a factor of x, then f of a is 0. So if that is a factor of that, then when you put 2 into this, because there's a 2 here, when you put 2 into this, it makes 0. So that means if f of x is this, f of 2, which is just what happens when I put 2 into this, as I've done here, that equals 0, according to factor theorem. That gives me an equation here. And then I'll do the same thing here. Now this is not in this form, but essentially you're just looking for what x would make this bracket 0, and x is minus a half would do that. So f of minus a half, put in minus a half into here, get it all done, times everything by 4 to give yourself some whole numbers. And now this and this creates a simultaneous equation, which I'll then use. So there's my simultaneous equation. I'm going to take this away from this, or do this, take away this, I should say, to get rid of the p's. I think that makes this. And of course I can solve that for q. And then I go back into here. I put q into here to find p. Times everything by 3 is probably what I did here, because I don't like fractions. Collect that together, solve for p. And then it's asking for 2p plus q. I guess I can simplify that as well, actually. And then 2p plus q is just 2 lots of this, which is that, plus that, which gives us one of our answers. Good. Question number 3. Sketching, there's a lot of sketching in this paper. Firstly, I can sketch this. That's a quadratic with roots at -2 and 2. So that's nice and simple. It's less than 0 in between -2 and 2. So that's my first inequality. This is a cubic. Now, if you look closely, it's a negative cubic, because if you were to expand out the x cubed terms, you'd get a minus x cubed. So it's a cubic that starts up here and does an S shape down to down here. And its roots are at -4, -3, and 1. So it looks like that. Now, when is this greater than 0? Well, it's greater than 0 when x is less than -4 over in this section. But that's kind of irrelevant, because I have to satisfy both of these. So this is mutually exclusive with that. Like it doesn't, like these two things don't work together, so this is irrelevant. It's also greater than 0 in between -3 and 1, and that's much more helpful, because these two things do go together, except they only go together between the highest low point, which is -2, and the lowest high point, which is 1. And so we get this is our inequality that works for both. Number 4. Okay, so a geometric progression goes ar squared, ar cubed. You're just multiplying by some factor r each time as you go along the sequence. This is the sum of a geometric sequence as long as r is less than 1, which I'm assuming it to be, and that apparently equals 12, which I can quickly rearrange to be this. So that's going to be helpful. A arithmetic progression goes a plus some number d, and then you add another d, and then you add another d, and so on. So that's an arithmetic sequence: first term, second, third, fourth, fifth, sixth. And apparently the first term of the geometric is the same as the first term of the arithmetic. That's why I've called them both a. The second term of the geometric is the same as the fourth term of the arithmetic, so those two are the same. And likewise, the third term of the geometric is the sixth term of the arithmetic, so I get this as well. Now, this is a simultaneous equation in 3 variables. I have 1 equation here, 2 equations, and 3 equations. So I should have enough equations to solve this because I also have three unknowns, A, R, and D. And it's just a case of eliminating them down. Now it's asking me for the first term of the geometric progression, which is A. So I need to, it would be most efficient for me to eliminate R and D and find A first, because that's what it's essentially asking me for, just the first term of the alphabet of the geometric progression, which is A. So let's look at these two and eliminate D first. If I times this by 5 and times this by 3, I can then imagine I stack this one on top of this one and take them away. I get on the left-hand side this take away that, and on the right-hand side I get this take away that, which is 2A, and this take away that, which is nothing. So there we go, I've eliminated D already, and now I'm going to work with this equation and this one. So that's a similar equation in two unknowns, A and R. Now I'm just going to rework this one into that. I hope you can see what I've done there. And now I really don't want to work with fractions. I could divide all this by 12 and then shove the R into here, but I really don't want to be dealing with division by 12 and then squaring it. That would be annoying. So I'm going to do something a bit more intelligent, which is I'm just going to multiply this whole equation by 12 first. And I'm going to put the 12s in very careful places. I'm not going to multiply 5 by 12. I'm just going to write it as 12R. And likewise here, I'm not going to multiply 3 by 12. I'm just going to write it as 12R. I'm just going to separate out these R's. And then, of course, this times by 12 is 24A, so that's fine. But now I can shove in these 12R equals 12 minus A. I'm just going to replace those 12R's with 12 minus A's. Now I can expand out. And now I'm going to carry this 24A over to the other side. And I'm also going to, I think I'm going to rewrite this, as 3 lots of A times 12R. Because again, that means I can shove in another copy of 12 minus A. I've also moved this 24A over to make this. And that's good. Now I can expand that out again. And now something really nice happens, which is that this cancels with this, and this also goes nicely with that. And I get this very simple equation here. And again, I've just got one more R to eliminate, but I can do that via this. Now I could go in a different direction here. I could say, well, I know A isn't 0, is what I could do. If A was 0, then the first term of the geometric progression would be 0, and then whenever you multiply the y, you just get a bunch of zeros, which would make this not make sense. So A can't be 0, so I could just divide by A squared here and solve for R. And then I could go back into here and get A, and that's what I thought about doing. But then I was like, nah, let's just times this whole equation by 4, and then put this 12 next to this R again, and then shove in this again. And then I can just get an equation with A, and then I don't need to bother finding R. I get this, and again, at this point, I'm going to make that same argument where I know A is not 0, because then this whole question wouldn't make sense. So I can just divide by A squared here, and I get my answer. Okay, question number 5. So we've got a quadratic with symmetry at x equals minus a quarter, and it touches the x-axis at one point. So this means it has exactly one root, a repeated root. And it also means the discriminant is 0, which I think I'm going to use as well. Now, that means its roots, if we picture the graph in our head, if it's symmetrical around x is minus a quarter, which I could say is roughly here, that means that the graph must look like this, right? Like, there's no other option. It only has one root and it's symmetrical here. That means it must look like this. So I can use both of these facts. Let's use this one first. B is just 6, A is P, and C is minus Q. So I think I end up with this statement, which gives me this, which is cool. And now if I have the root at minus a quarter, what that means is when I put in x is minus a quarter, I get 0 out. So I should end up with 0 equals, and then I put in x is minus a quarter at the x's. And again, when I deal with this, that's going to make a 16th, because a negative squared is a positive. This is going to make minus 3 over 2, or whatever. And then I'm going to times by 16, I think, just to get whole numbers. But again, look, I've just ended up with another simultaneous equation. So I think this is probably the third time in 5 questions that I'm solving a simultaneous equation of some sort. I can make this into minus 9 over q, and then I can shove that into here to just end up with an equation in terms of q, times everything by q to get a quadratic in q. I think I've just rearranged the order of the terms here, and then I've noticed that it factorizes really nicely into this, and therefore q solves to be minus 3/4. Then I go back into here and I solve for p, just timesing by 4 there, cancelling the negatives, divide by 3, which makes 12, and then the answer, the question is p plus 8 lots of q, so it's 12 plus 8 lots of that, which is just 6, and I get my answer. Excellent. Number 6, find the maximum value of that. Well, finding the maximum value of 1 over a, you want to minimize the a, right? Like you want to make this as small as possible, and then that max is the 1 over it. So essentially my objective here is to make this function, let's just call it g of x, as small as possible. Now this is easier maybe to see if I replace, this is a quadratic in 5 to the power x, but I might just replace it with y's. But this quadratic and this quadratic are equivalent if you just say y is 5 to the power x. Because then y squared is 5 to the 2x, and so on. And I can minimize this fairly easily. There's a couple of ways I could do it. I think I've just chosen to differentiate. No, I haven't. I've just chosen to complete the square. Excellent. So I've said, well, what's half of this? 2, square root 4. So this is a nice square quadratic here. So I'll make it into a square quadratic. I've got plus 3 here. This minimizes when y is 2 and takes a minimum value of 3. And I think the reason I did this is because it now doesn't matter that I'm in the wrong variable. The minimum value of this is 3, and it doesn't matter whether you go back to x's here. The minimum value is just 3. It's not asking me when, for what value x does this maximum value happen, or the minimum value of this for the maximum value of that. It's just asking what it is. Now I've worked out that the minimum value of this function here is 3. Even though I've done it in a different variable, it doesn't matter. Because I'm not looking for the x, I'm looking for the minimum value of the whole thing. So therefore, the maximum value is 1 over 3, which is obviously a third. Okay, number 7, it's another simultaneous equation disguised. This 8 is 2 to the power 3, and then of course I can multiply out those, and now I've got matching bases, so it's just 3x equals that. There's my first equation. This here is 2 squared to that. This is 2 to the 4 to that. This is 2 to the 3 to that. So I'll change all those. Oh, I also divided this by 3. Fine, whatever. And then I'll expand out all of those brackets. Now this is 2 to this divided by 2 to this, which means, of course, you take away the powers. When you've got the same base and you're dividing, you take away the powers. So that's going to be this. Don't forget to take away this 9. That's why I put it in brackets. Well, that's just going to be 2 to the y minus 5. And again, same base, compare the indices here. That gives me that equation. And this is just a simultaneous equation, isn't it? So there it is. I think I've just rearranged that one slightly to get there. I'm taking away 2 from both sides, taking away right. I'm sure you can follow. Take this away from that to get minus x minus y minus y is 0. This minus that is 10. So x is minus 10. Put that back into here and you get y is minus 13. What's the value of the 2 added together? Minus 23. Excellent. 4 simultaneous equations in 7 questions, possibly. Okay, this one. The function f is defined as this. Now this is kind of interesting. I've done this in a very weird way, only because they've presented the quadratic in a weird way. They presented it in factored form, which gives you the roots at p and minus 2. So I thought, well, why not just use that? I've got roots at p and minus 2. And it's also a negative quadratic, look, because of a negative x squared here. So it goes upside down. And now it's saying find the complete set of values for which the maximum value, so this value here, is less than 4. Well, okay, so what's the x value at the turning point? Well, quadratics is symmetrical. This one doesn't look like it because I've drawn it badly, but it's just a sketch. But quadratics is symmetrical around the turning point. Now, if the roots are at minus 2 and p, that means the turning point is the average of those two things. So the x-coordinate of this turning point is p minus 2 over 2. You just add the roots together, which gives you p plus minus 2, which is p minus 2, and divide by 2. So that's the x-coordinate of the turning point. So all I need to do to find the y-coordinate of it is put that into here, right? So I'm just going to put this value into my function, which can be this. This is p over 2. Sorry, this is 2p over 2, I guess. And essentially, sorry, before I do that, I just want this to be less than 4, right? I just want this thing here to be less than 4. That's what it's asking me. Now I can put this into one fraction. That's 2p over 2. That's 4 over 2. I can put these together now. And kind of really nicely, they end up just being the same thing, which means this is just going to be this thing times by this thing, which gives me p squared plus 4p plus 4. This is going to give me a 4 on the bottom, so I'm just going to multiply by 4 to make this. Move the 16 over, and this factorizes very easily to this. And now maybe be a bit careful here. I mean, I can already see the only one with answers 6 and 2 is this one, so it must be this. But just be a little bit careful to make absolutely sure. This is a quadratic in P. It's a positive quadratic this time, has roots at 2 and minus 6. And I want it to be less than 0. So that is indeed between minus 6 and 2, which is exactly what this says here. So yeah, quite a nice question, that one. Question 9, more quadratics. So this factorizes as this. Okay, fine. That means that alpha or negative alpha times negative beta is 9, but the two negatives cancel, obviously. It also means that minus alpha plus minus beta is minus 14 when I expand that out, but of course cancel all the negatives for this. Now, what quadratic can we factorize as that? Well, let's just expand this out first. If I expand this out, I get this. Again, those two negatives cancel here, and then I've just factorized the x together to make this. Now, I can just root this here. If I just root both sides, I get, well, I can collect these two roots together, obviously, because that's just how roots work. But I can root this whole side to just be this, which tells me that it must be one of these three first, because root alpha beta is 3. So it must be one of these ones here first. Don't worry too much about the negative 3, because negative 3 isn't an option, so I don't have to be concerned about it. Now, what about this thing here, though? Is that a 10, a 14, or a 20? Now, be really careful here. When you root both sides of this, you get this. You do not get that. So that's the, you know, when you root this thing here, you can't root these individually, like this. So it can't be B. And I'll just quickly show you why. Like 3 plus 2 is 5, I'm sure we can agree. But that doesn't mean that root 3 plus root 2 is root 5. And we can see this easily if we just put in some numbers. I know that's about 1.7, that's about 1.4. I'm guessing that's about 2.2, but clearly these two things don't equal that when you add them together. But what this does tell me is that you get quite, like this and this is quite a lot more than that. So even if my estimations are slightly wrong, it's definitely still not correct, because this and this make a lot more than that. And in fact, we can get some feel that root alpha plus root beta is quite a lot more than root alpha plus beta. Like root 3 plus root 2 is quite a lot more than root 3 plus 2 or 5. And so for these two, I know root alpha plus beta is root 14. I know that because I've just rooted both sides of this properly. But that means that root alpha plus root beta, I think, is more than root 14. And the only option that's more than root 14 is root 20. So it must be this one here. So quite a hand-wavy argument, but you know, in TMUA you don't have a huge amount of time to prove things properly. So often having a feel for it and using intuition is a good plan. Question number 10. So we can very quickly sketch that. That's this. It's a translation 3 across and minus 5 down, or just 5 down, I should probably say. Well, that looks a bit like this. And I also know how to do this with curves. I just put the minus 3 into the x bit, and then just take away 5 at the end. So that's the red graph's equation. Then it reflects in the x-axis, which looks a bit like this. And a reflection in the x-axis just means putting in a negative in front of the entire function. So that must be the equation, the green graph. And now this is the most difficult bit. Stretch parallel to the x-axis, scale factor 2. So that's stretching outwards, left and right, scale factor 2 like this. But be careful here, because when you're doing that, it's actually f of a half x. Like to stretch it out, you use a half. If you were to squash it towards into the y-axis, then that would be a 2 here. It's a half actually when you're stretching it out. So everywhere I see an x, I'm going to replace it with a half x. So I'm going to take the green equation and I'm just going to replace the x with a half x. And this is the equation for this black curve here. Of course, this is not one of the options, but all I have to do is tidy this up. So obviously this squared is this times this. This is going to make a quarter x squared. Then I'm going to take away 3 over 2x or 1.5x, but then take away another 1.5x, and that just takes away a whole 3x. And then this, of course, is plus 9 times this bit only by 4. Well, that ends up making all this quite nice. That's just this. And then take away the 5, obviously. But then I've still got this negative that came out all the way at the front. That's the last thing I'm going to deal with, which is going to be a negative x squared plus 12x, negative 31, which is a good. Number 11. Another quadratic. Seem to have just dealt with quadratics and simultaneous equations as being the entire thing. So I've got this region R, this region S. Apparently R is equal to S. I'm just going to find the value for Q for which makes that work. Now, firstly, I need the equation of this curve here. And that's fine because, again, if it's got roots at 2 and Q, that means the equation is this. It's also clearly a positive quadratic. So I know this is the equation. I can multiply that out. And this is my equation for this function. I've put the 2 and the Q together here because I'm going to probably be integrating this. So it's useful just to keep one term of x rather than two separate ones. Now, it's tempting to do this, right? And just be careful to make sure you've understood what I've done here. I'm integrating between 2 and 0, the function, and I'm saying that must be equal to the integral between Q and 2. Now, there's also a negative here, and that's just because, remember, when you integrate for an area below the x-axis, that's going to give me a negative answer. So for this integral to actually equal this integral, I'm going to have to stick another negative in front. But actually, this is kind of irrelevant because this is not what I'm going to do, because actually there's an easier way, which is if this area is equal to this area, if R is equal to S, then the integral between Q and 0 should just be 0, right? Because this negative area is going to cancel with this positive one. And this is a much easier integral. Rather than doing two of them like this, I'm going to have to do much less work if I just look at this instead. So that's what I'm going to do. Integrate this as x cubed over 3, integrate that as x squared, and then divide all this by 2. Obviously just stick an x on the end, and then I'm just going to have to substitute in the q because all of these contain x's, which means it all just goes away when I put in 0. So I'm saving myself quite a lot of work not having to substitute in these 2's to do this. So that's fine. That equals this apparently. Yeah, sorry, when you put in q to this, you just replace all these x's with q's and then the zeros are so you just end up with this. Get rid of the fractions, I guess, I think I times everything by 6, yeah, to get rid of both this and this fraction. Just make sure you are okay with what I've done there. Times everything by 6, and then, yeah, I think you can just get rid of q squared here, right? Or I can multiply out the brackets first, then I can tidy it up. Then I think I can get rid of the q squared because, of course, q being 0 is a trivial solution, right? It's also not allowed. So I know q isn't 0 because apparently it's bigger than 2, which means I can just divide by q squared here to get this, which of course makes q 6. Question number 12, more sketching, which is excellent. I'm going to sketch both of these because essentially what this question is saying is, when is the graph y equals 3 cos x equal to the graph y equals root x? Because of course if you're answering this, you would just set these equal to each other, which would give you that. So let's draw these two graphs. Here's the graph of 3 cos x, very roughly. It's supposed to be a terrible sketch because it's just a sketch. You just need to get an idea for what it looks like, not a perfect drawing. Now, root x, that's not plus minus root x, that's only root x, which means it just looks a bit like a log graph, except it starts at 0, there's no asymptote. It starts at 0 and then sort of heads up slowly this way. I should say as well, this cos graph peaks at 3 and minus 3, and then the roots are, of course, pi over 2, 3 pi over 2, 5 pi over 2, and so on. Now, this root graph looks a bit like this. You should just know what this graph looks like going into something like TMUA, or at least have a feel for it. Now, the problem is, does this look like this? Or does it rise much more slowly and look something more like this? Because, of course, that changes the number of roots that it might have. Like, it has minimum 1. Like, even if it rises really, really fast, it has 1 root here somewhere. But does it have more over here? And the way that I'm going to analyze that is I'm going to pick a value such that I can plot this root graph more accurately. Now, if I just pretend, well, when x is 9, I know that y is 3 on this graph. So if I could find 9 on this x-axis, then I could say that this graph is up at the peak of where these graphs peak up here, right? So when x is 9, wherever that is, this graph needs to be here, in line with one of these peaks. Now I'm going to pretend to be an engineer for a moment and say that pi is 3, because that means that this value here, 5 pi over 2, is 7.5. Now I know it's a little bit more than that, but it's not going to matter too much, because 7 pi over 2, if pi is 3, is about 11.5. It's actually not, it's 10.5. That's a mistake. 7 times 3 is 21, divided by 2 is 10.5, but it's not going to be, it doesn't matter, because all that means is x is 9, I know must be in between these two roots somewhere. So x is 9 is somewhere in here, which means when x is 9, remember on this graph, y is 3, which means this slowly rising graph goes through this point here, which means it looks a bit like that, and I get 1, 2, 3 solutions. It never comes back down, and it's already over the peak as soon as you pass 9 of the 3 cos graph, which means it never touches this graph again. It just goes up like this and has 1, 2, 3 roots. Yeah, cool. Number 13, which is number 12, number 13, binomial expansion. So the way that I like to think about this is if you lined up all of these, all 7 of them, I've only bothered to write 4, I think of this as kind of bouncing along, things taking whatever you want. So you can take 7 ones if you want to, you can take 6 ones and an x somewhere, or 3 ones, 2 x's and 2 y squares, whatever, but you need to take 7 things, and 7 things come together as you bounce along, taking one thing from each of the 7 brackets to make a full term. Now what I'm going to do is I'm going to just colour in 1 plus x as a red thing. I'm going to say actually this bracket only contains 2 things. It contains 1 plus x and it contains y squared. Now if I want the coefficient of y to the 4, I can only take 2 y squareds, which means I need to take 5 1 plus x's. So I need to take 2 y squareds and 5 1 plus x's. Now there are of course 7 choose 5 ways of doing that, or 7 choose 2, but that's actually the same thing, and maybe our working will tell you why. But I need to take 7 choose 2 or 7 choose 5 of 5 of these, which is of course means that to the power 5, and 2 of these. And that clearly is going to be the y to the 4 term. I'll deal with this in a second. Now 7 choose 2, n choose k is this. So 7 choose 2 is 7 factorial over 2 factorial, 7 minus 2 is 5 factorial. And of course this is why 7 choose 5 is the same thing, because if you were to put k as 5 in here, you'd get 5 factorial, and then 7 minus 5, which is 2 factorial, and you just end up with the same 2 terms. So that's why it doesn't matter whether I choose 7, 5 or 7, 2. Now, of course, this I can do in my head quite quickly, because this is just 7 times 6 times 5 and so on. This is 2 times 1, and this is 5 times 4 times. And then what we can do is we can say all of that bit cancels with all this bit, and all I'm left with is 7 times 6 divided by 2 times 1. 42 divided by 2 is 21. So this is 21. And now what I want to do here is I want to just collect that y to the 4 over here and say, well, actually, all I need is I need an x squared term out of this. So I've got this bit here, and I'm just looking for my x squared terms from here, and then I should be fine. But again, that's just choosing to get x squared out of this. I'm choosing 3 of those and 2 of those. So that's 5 choose 3 or 5 choose 2. It doesn't matter how you say it. With 3 of those, 1 to the power 3, which of course doesn't do anything, x squared. And that's giving me x squared. Now 5 choose 2 is going to be 5 factorial over 2 factorial, 3 factorial. Of course, the second half of the 5 factorial cancels with the 3 factorial, and you're just going to get 5 times 4 divided by 2 times 1, which is 20 divided by 2, which is 10. Just verify that on your own if you want to, but I know I'm going to get a 10x squared out of this, which of course times by this to make a coefficient overall of 210 x squared y to the 4. That's going to be my answer. Number 14, bit of integration here. I think the second time we're doing integration. Let's sketch this first. Again, this is going to be a shocking sketch, but that's just a straight line that goes through the origin, gradient m. This is a cubic, the simplest cubic, which looks a bit like that. Again, a shocking sketch, but just really goes to show you how you don't need to plot these. We don't need to take our time over either. You need to just get yourself an idea for what the thing looks like. Now, what this is asking is saying the area enclosed by these graphs, which are these 2 areas here, total 6. Now, this is entirely symmetrical, which means each of these little areas is 3. Which means all I need to do to find the value of m is find this intersection and then integrate between here and here and say that that answer is 3, and I should be able to get m. Now, what's the intersection point? Well, that's just when mx equals x cubed. Now, of course, there's the trivial solution of 0, so I can get rid of x's. I can get rid of one of the x's. Now, of course, I can square root, and I'm finding that my intersection point is when x is root m or minus root m. Of course, it's symmetrical, which means this point here is the point when x is root m. And what's y? Well, y is just m times root m, which is m root m. So this is the point, root m root m. Now I could do two lots of integration. I need to find I want to find this little area. I know it's 3, but I want to express it anyway. So I could integrate the line between root m and m, but it's just a line, which means the area underneath that is just a triangle, right? And it's got a base of root m and a height of m root m. So the area of that triangle is just a half times root m times m root m, half base times height. And now I will take away the integral of x cubed between 0 and root m, and apparently that answer is 3. Now this is nice because root m times root m is m, times m is m squared, so this is just m squared over 2. This integrates to x4 over 4. Put in root m, now root m to the 4 is m squared, so I just get m squared over 4. Of course, when you put 0 in, nothing happens. This is good, that's just m squared over 4 times by 4, and now this is just some very basic understanding how surds work. I know that I don't need the plus minus because I'm just looking for the positive m here. Of course, that's root 4 root 3, which is 2 root 3, and that's my answer. Number 15. First thing to think about here is just be careful. This is the log law. This does not apply to this one here. This is not log 2x to the 4. This is log 2x all to the power 4. So that's different to this rule here. So I can't use that straight away, but I can use this law here. It's just disguised a little bit because 1 over x, of course, is x to the power minus 1. Now 2 to the 6 is just 64, so I've written that. But now, of course, I can move this power, this minus 1, down to the front, and I get minus log 2x, but I'm squaring that, right? And when you square a negative, it's just the same as if you were squaring the positive. So I can get rid of that negative sign. And now, it's a little bit hard to spot, but this is actually just a quadratic, because if I just pretend y is log 2x, I get y to the 4 plus 12y squared minus 64 is 0. And I can factorize this very simply. It factorizes to this because 16 times 4 is, or negative 4 is negative 64, and they add to make positive 12. And I can solve this very simply, either this or that. Now this doesn't work in the real values because I can't square root negative 16. This does. The root of 4 is plus minus 2. But of course that means log 2 of x is plus minus 2. So either log 2 of x is 2 or log 2 of x is minus 2. And what this is saying is 2 to the power 2 is x, which of course means x is 4, or 2 to the power negative 2 is x, which means x is a quarter. And the difference between, it's asking for the difference between the two. The difference between 4 and a quarter is 15 quarters, because that's 16 quarters, that's 1 quarter. Difference is 15 quarters. Number 16, the circles question. Let's graph these first. So that's a circle, center minus 2, 1, radius root 3. So that's probably about there. Notice how I haven't had it touch this line because it's 2 away from the y-axis and only root 3 in radius. Root 3 is slightly less than 2, but like it's only 1 away in this direction and root 3 is bigger than 1, so it looks pretty much exactly like this, I think. This one has center 4, 1, radius root 3, so that's over here somewhere. And then we've got this straight line, which is tangent to both of them and has a positive gradient. So it could have been this one, but it's got a positive gradient, so it's this one. And it's asking me for the acute angle between L and the x-axis. Essentially, it's just asking me for the gradient of the graph, but it's asking it in terms of tan theta. Now, this question took me a long time because I went down a very dark path of doing a lot of algebra before realizing that you can do this in about 4 lines. And the reason that you can do that is because, well, the radius of these circles is root 3, as I've already said. Now, the distance between the centers is just a flat distance of 6 from minus 2 to 4. And of course, this is an entirely symmetrical picture around the line x is 1, because that's 3 away from this and 3 away from that, which means each of these distances here is 3. And the last thing I need is that tangents meet circles' radiuses at 90 degrees. So I think I have this picture here. And like this angle here, theta, is the angle they're talking about. The angle between this line, which is parallel to the x-axis, that's fine, and up to the line here. So that angle is the one I'm looking for. I already put in a root 6 here because I've just done a bit of Pythagoras on that triangle. 3 squared minus root 3 squared is 6. Rooted is root 6. And now I'm just looking for this angle. And of course, tan of this angle is opposite over adjacent. So tan of theta is root 3 over 6, or over root 6. That's none of the answers, but that's okay because root 6 is root 2, root 3. Cancel the root 3's, and then, of course, I can rationalize this times by root 2 over 2 to get root 2 over 2. And that's going to be the answer of C. So yeah, great question. It's very possible to go down a very dark path with a lot of algebra there, but just thinking about it pictorially gets it done a lot faster. Question 17, more quadratic work. Yeah, find the complete set of graphs, pointers, terms. Okay, cool. So let's graph this again. The first thing I think of this when I say 2 points of intersection is that the discriminant has to be bigger than 0. That's what 2 points of intersection mean. So let's set this to equal this, rearrange, and now this is a quadratic. It doesn't really look like one, but if you let y equal root x, then that means that when I square this, I get x, which means y squared is x, and I get my quadratic. I need 2 points of intersection, which means my discriminant needs to be bigger than 0, which means b squared minus 4ac is bigger than 0. That's a is m, b is minus 1, and c is c. So I get minus 1 squared, minus 4 times m c is bigger than 0, which is this, rearrange for this. And now you maybe want to be a bit careful here, and this is where the graphing comes in. Now it's easy to just divide by 4c and say this, which is one of the answers. But you need to be careful of two things here. Firstly, what if c is less than 0? Because when you divide by c, you need to flip this sign, which would actually give you another one of the answers. But also the other thing I notice is that there's this answer here, which has the thing that I have, m less than 1 over 4c, but also has this qualifier. And I haven't really justified why this needs to happen or why it doesn't need to happen. So I need to be a bit careful just before selecting the answer of D here. And yeah, this is where the graphing will come in. If I were to graph this, we've already graphed this one here. That's one of the, that sloping thing here. Now, this is just a line, y-intercept of c gradient of m. Now, here's an example of having 2 points of intersection. And the thing is, there's two things going on here. If I just move this line around, the first thing is, if I make c less than 0, I don't think I can get 2 points of intersection, right? I can only get 2 when, look, that c becomes slightly above 0. If c is less than 0, even no matter how steep I make this, I can't really seem to make 2 points of intersection. So that kind of justifies why I don't need to swap this sign. But the other thing is, and you can see, spoilers here, the answer is indeed A. M bigger than 0, if m is less than 0, if we've got a negative gradient to this red line here, of course I can't get 2 intersections. I could only ever get 1, right? M has to be bigger than 0 for 2 intersections. So that's where this extra qualifier comes in, and we get the answer of A. So yeah, you just need to think through that a little bit more carefully to get the correct answer. So never just select it straight away, just think through it a little bit carefully, particularly if you've got time left. Question 18, you can see I've already got my axes out because I'm going to start sketching. The first thing I think when I see this here is that reminds me quite a lot of this thing, which I think is going to be very helpful. They've got it the other way around, so I'm just going to say it's minus cos 2x is this. Now I know I can plot both of these things. Cos x between 0 and 180 looks roughly like this. Again, it's a terrible sketch, but that's the whole point. Which means minus cos x, flip it in the x-axis, looks like this. And therefore minus cos 2x, that's a squash in the parallel to the x-axis of factor 2. So that essentially means you just draw an entire cos graph within the space provided. So that's my graph there. And now what about this graph? Well, that's just the cos graph, but always positive. So it does the same thing here, but then instead of going down to the negatives, it bounces back into the positives. So it's actually just these two segments of graph put together. And now, okay, so we can easily see that we have two solutions. So it's one of these two answers. What do they add up to? Well, notice how it's entirely symmetrical about this point 90. And so it's fairly easy to argue no matter where these 2 points are, they must add up to 180 because one is some amount less than 90, the other is an equal amount more than 90, so their average is 90, you may as well just be adding two lots of 90. So the answer must be A. Number 19, possibly the easiest question on here, not really sure why it came so late. Let's quickly graph this because graphing stuff is fun. It's a positive quadratic, and the only thing I really know is that it goes through minus 52 as its y-intercept. Now what that means is I can infer that it has one root below 0, which is completely irrelevant because I'm looking for positive integers, and one root above 0, which is much more relevant. Now, if I could find this root, all I'd have to do to find the smallest positive integer for which the graph is positive is round that root up to the nearest whole number, and then I find the lowest whole number that the graph is positive for. And I know it must be that because this root is down in the negatives because of this y-intercept, which means all of this is irrelevant. So all I need to do is find the root. I can't remember how I decided to do that. Oh, I completed the square. Okay, so I halve this number, squares that very quickly. It doesn't take very long if you're good at squaring numbers. Put those two things together, and now, of course, move the other thing over and square root and move this over, and this is my root here. Of course, this root here is 26 plus root 728, because the negative would give me this one. Now, just quickly here, I'm going to note that 27 squared is 729. The reason I tried 27 is because I know what I previously learned was 26 makes this. So I'm going to try 27, but 27 is too high, which means this is ever so slightly less than 27, which means if I just replace it with 27, in other words, make it ever slightly bigger, I get x is less than that thing. So this root here is slightly less than this. This root here is slightly less than 53, which means the integer 53 is just slightly to the right here, and that's the lowest integer for which this graph is positive. Very last question, for how many values of A is that equation satisfied by two distinct values? Now, I've got to admit, this is the only question on the paper that I got wrong first time, because it has a very nasty trick to it, and I'm not entirely sure how you're supposed to spot this without being just a mega genius. Now, the first thing I notice is that, okay, I've got this in factored form. So for this to be 0, either x minus a is 0, which means x is a, and that gives me a solution, right? So for any value of a, I'm going to get one solution from this thing right here, of x is also a. So when I'm solving this to be 0, I'm kind of looking for one solution to this, because I already have a solution. Like for any value that I pick for a, I get the one value of x back, and I want two values of x. So I'm kind of looking for just a single extra value here. Well, okay, let's solve this. I think I completed the square again because I was just feeling weird. Halve this number for minus 0.5, square it. Let's move those two things over and then square root. And now, okay, well, what I've said is I've already got a solution up here, so I just want one solution from this, which means if I could make this entire surd 0, I'd just get x as 0.5. Well, to make this whole thing 0, I choose a as 0.25, right? And that means I get 0 in here in this root, and I just get this answer. But of course, I've already got this answer of if a is 0.25, x is 0.25 gives me a solution. But if a is 0.25, x is 0.5 gives me another solution. So the x is 0.25 gives me that one is 0, and x is 0.5 gives me this whole thing is 0. So I've got two distinct values if I choose a as 0.25. So that's when I ticked B as my one value of a, which gives me two distinct values, except that turns out to be wrong because there's a super sneaky solution here, which is what happens if you just choose a to be 0. And now let's look at this thing first. Firstly, if we choose a to be 0, we get a solution of x is 0 from the first bracket. That's fine. And now what happens if we choose a to be 0 here? Well, we get 0.25 minus 0, which is 0.25, but the root of 0.25 is a half, because it's the root of a quarter. And of course, this gives us either 1 or 0, but we've already got the solution of 0 from the first bracket, so therefore we've got two distinct solutions for x, 1 and 0. So there are actually two values of a that do this. This one, which I found, and this one, which I have no idea how you're supposed to find. I just looked at the answer scheme and saw that I got it wrong, and then tried to think how I possibly got this wrong until I just tried 0 and it managed to work. Maybe other people can add some flavor to how you're supposed to figure that out by yourself without looking at the answers, but I would have totally just selected B and moved on from that.